Well, so hello everybody, good afternoon, and I have the pleasure to chair the last session of the data analysis. I'm Sweta Shah from Hannover in Germany, with all the fires blazing around me, so not to affect our Earth with more adverse effects of climate change, we are organizing the entire LISA Symposium online. And yeah, so let's begin the session. We've got MURATORE from Italia. She's a former pupil of Stefano Vitale, and she will tell us about the null channels of TDI. So Martina, the floor is yours.
Thank you so much for the invitation, and thank you for giving me the opportunity to present my work. So I will share the screen. Okay. So I'm going to speak about the effectiveness of the null channel as instrument noise monitors for LISA. I want to underline that this work has been done in collaboration also with Olaf, HARTWIG, Daniele Vetugno, Stefano Vitale, and Willa Joseph Weber. I just want to really give you a quick recap about what has been done, what has been said so far. So we know that LISA is dominated by the laser frequency noise, and Jean-Baptiste nicely introduce us this topic on the 26th. Just to show you what I mean, here reported a PSD, and you can actually see that the noise of, in case we don't do any kind of laser noise reduction, the level of the raw data are the one that I reported here in red. Then if you're able to apply this post-processing technique called time-delay interferometry, we are then able to reduce the level of the noise lower than the so-called requirement that are the one that I reported in black. After this, we have to apply other pipeline, this so-called initial noise reduction pipeline. And this one actually helps us to reduce other sources of noise, like the clock noise, the tilt to length, or the space shifter. And we will see a talk regarding that by Olaf, HARTWIG. And then we also, you should also have seen many talks on the LISA instrumentation section on the 26th. What I would like to say is that, so at the end, we are going to be left just with two main sources of noise, that are the acceleration noise and the optical metrology noise. And I will focus on these two kinds of sources of noise for my talk. So to have an idea, this is actually the kind of secondary noise that we see in the so-called time delay interferometry X, that is the standard TDI channel used for detect gravitational waves. So if you look again at this PSD versus frequency, what you can notice here is that at the high frequency, you're actually dominated by the optical metrology noise. That is the blue data here, where I superimpose the analytical model. Instead, the low frequency for this TDI, you're actually dominated by the acceleration noise. I did the simulation running the LISA instrument. That is one of the tools that we use in our LISA community. And this is the level of the acceleration, the optical metrology noise that we actually are currently using for the as a requirement. So why I'm showing that, just to introduce the topic that is actually important for us to need to know the instrumental noise. Why we care so much in doing this research and these studies. So in general, in case we are looking for sources with high SNR, actually knowing or not having a good knowledge of the noise doesn't make such a big difference. Different is the case when we are looking for sources like the stochastic gravitational wave background, because as you saw by the talk on Nicholas Canesis yesterday, we can just give a simple example, reporting the standard characteristic string for LISA here. So in case we just in case we are like, we have our data, we actually just apply the PSD of our data. What we actually going to have, if we just consider the galactic background, ignoring all the other sources, this is actually the level of the data of your PSD that you're going to have. So you're going to have this kind of bump in this frequency. Instead, in case you will just have noise without any kind of signal, the kind of sensitivity that you're going to have is actually this green one. So what the point I want to make here is that if you would like actually to try to be able to understand the difference between the presence of a galactic background and on your noise, you have to be able to somehow try to disentangle what is the noise from your stochastic gravitational wave background. Unfortunately, for LISA, we cannot apply a technique like cross correlation. That is the standard technique that have been using for LIGO. So, and Virgo. So we have to try to use a different way to characterize our noise. So there are actually two possibilities to characterize our noise. One is the so-called pre-flight modeling. So we can try to characterize the noise by pre-flight estimation and modeling and campaign. Otherwise, you can actually try to look for particular TDI combinations that are called new channels. And these combinations are characterized by suppressing the gravitational wave signals, but they still carry some information on the noise. So regarding the first point, I just want to quickly report what has already been said. So if we actually try to do an in-flight estimate on pre-flight estimation of our noise, what happened? So the main problem is that we are not sure that we are able actually to model and predict very accurately what is going to be our model once LISA will fly. An example we can just see here, where I just take this image from the talk of Daniele Vetrugno, where we actually compare the model of the LISA pathfinder that we have, and actually the kind of noise that we are able now, that we have knowledge at the moment. So as you can see here, there is part of the noise that is actually still not understood. This is actually just show you how difficult it is actually to try to predict very accurately what is going to be the model, what is going to be the noise in flight for LISA. In addition, we have also to underline that we cannot, unfortunately, do all the possible kinds of testing on ground for LISA, because there is some part that actually cannot be tested. For example, the longer if interferometry, we cannot do an end-to-end testing. Having said that, one of the possibilities then is to try to use these new channels. And here I just reported a sensitivity plot that compare the different sensitivity of different TDI combinations. So regarding what is the meaning of this different TDI combination, again, I invite you to look at the Jean-Baptiste talk that nicely explain the different TDI combination. And again, how we can relate this different TDI combination. There is going to be a talk by Mauro Pieroni, so I'm not going to enter into detail. Here, I just want to show in particular these two curves. So one is the standard TDI-X. As you can see, it's the more sensitive to gravitational waves. Instead, the so-called null channel that I would like to use is this one, it is the TDI-zeta. And you can see that it's much less sensitive to gravitational wave compared to X. So having said that, if we then try to estimate how actually our noise will propagate in the TDI-zeta, I reported here, again, the PSD, considering the optical metrology noise, that is the blue one, against the acceleration noise. So what you can see, if you actually compare the new estimation of the noise compared to the zeta, to the X channel, unfortunately, the zeta channel is totally estimated by the readout noise. Instead, the X channel, we see that is dominated by the acceleration noise at low frequency, but it also dominated by the OMS noise at high frequency. So from this, comparing the two plot, it actually looks like that you can use the zeta channel to try to estimate the noise of the X channel at high frequency. If you want to understand why there is this difference in behavior, we can just quickly look at these two formula, in particular how the noise propagates in TDI X zeta. And we can actually see that the reason why in TDI zeta we don't see acceleration noise at low frequency is that because there is this factor that actually, let's say, reduce the acceleration noise at low frequency. And this is why the TDI zeta is dominated mostly by OMS noise. So again, so what, having said that, we would like then to try to see what we can do using this new channel to try to do a kind of in-flight estimation of our noise. So just to give you an idea about what order of the optical metrology noise we should have in the TDI zeta in order to be able to estimate also the acceleration noise in this channel, we actually computed that in order to zeta to be also dominated by acceleration noise at low frequency, like the TDI-X, we will need an OMS noise of this level. And you can see that there are many order of magnitude between the OMS noise that is required at the moment for LISA and the idealistic one that we would like to achieve. So it actually means that unfortunately we cannot do, at the moment it looks like that it's very unlikely that the TDI zeta can estimate the acceleration noise at low frequency. So what the proposed solution that we then try to do is to try to suggest a different approach at the problem, and so try to avoid to use, for example, many approximation, many assumptions that people were doing so far in order to try to use this new channel in order to try to estimate the stochastic background, assuming the knowledge of the noise. So what we try to do is to try to compute a formula that does not arrive of any assumption of the actual noise level, of the test mass and the optical metrology noise. And we also we find it out that there is a way to combine the data that they are actually independent from time, and they also are robust against non-stationarity. Unfortunately, the problem of this is that we also stay in the same assumption that the noise are not correlated, because as I will explain to you later on, is that we cannot use any new channel to try to estimate uncorrelated noise. So in order to try to find this, to try to understand how zeta can actually estimate our noise in the X channel, we need to look for a function f, such that we are able to find an upper limit using the zeta channel. So upper limit means that we have to find a function that applies to our noise in zeta is actually bigger than the noise in X. This will tell us that for sure we are able to find an upper bound on the X noise. Just to show you what we mean for S zeta Sx, we can just write it down in simply the noise of these two channels, where S zeta is just made up of the sum of the acceleration noise multiplied by its transfer function, plus the sum of the optical metrology noise multiplied by its transfer function, and the same for zeta. So if you do some calculation, you're actually able to find this function that has the following value. I'm not going into detail of all the calculation, but in case you are interested, you can just have a look of this paper, the paper that we published and put in archive, but we are going to have an updated version in mostly 1 week. So just to do this overall presentation, so if you just look at the total noise in X, that is the green one, for our estimation, we saw that actually we are able to estimate the noise in the TDI X using the zeta channel by this far amount. So actually using zeta to estimate X tell you that this is actually the noise that you are going to get. Just to have an idea, you can actually do the ratio between these two estimation. You actually see that at low frequency, your estimation of the noise in X is a little bit above by the actual value of the noise in X. Instead, you are a little bit better, obviously, at high frequency, where your level is lower than 2 by between 30 milliards and 100 milliards. And this is actually expected because, as I showed you before, both the combination dominated by OMS noise at high frequency. So it's actually the probability that you can use zeta is better at high frequency than at low frequency. Here, I just want to show you very quickly why we cannot use the new channel to estimate correlated noise. So if you just write the intermediary variable, and Jean-Baptiste already on Monday already explained how you can build this variable. In our case, we build them using the optical metrology noise and the test mass acceleration noise. If you then actually use this eta to build your zeta channel, and here I reported the standard case of equal arm length, you can actually see that how these eta variable are combined. So for example, if we just take this eta 31 and eta 32, and you actually look at the plot on the right, you see that every noise that is common between these two optical bench or these two MOSA will directly cancel out. So this actually means that any new channel, for the way that they're built, actually cannot be used for doing any kind of estimation of correlated noise in the sensitive channels. So having said that, I would like to show you to conclude, showing how you can actually use this estimation of the upper bound of the noise to try to estimate the stochastic background, more than estimate, to try to give an upper bound on the stochastic background that we are able to see with LISA. So the first thing that you can actually compute is actually that using is an obvious estimation. So if you just take the TDI X, that is, if you just take the data that you receive with the stochastic background, you can just plot like a sensitivity curve, and you are sure that your stochastic background will never be bigger than what we actually observe. The second thing that you can estimate is the so-called detection threshold. And it means that using the zeta channel, you can actually say that this is the detection that I can estimate, and it means that in order to be able to distinguish the noise from the stochastic background, I need that my stochastic background is up to this curve. So if you really in reality, obviously, we cannot represent just the noise as I represented here, but what we can actually define is an upper bound, consider the realistic measurement that we will have. So in case of the TDIX, you will that's what you are going to estimate. You can say that your estimate is going to be bigger, obviously, than hypothetic model on the stochastic gravitational-wave background. So this computation rule out possible model that you actually are not seeing in your data. is that regarding the lower bound, what you can actually have, you can actually see that you are able to detect and distinguish your stochastic background if the difference between what you measure in X minus the new zeta channel that we estimate divided by the different transfer function is actually smaller than your stochastic background. So if the stochastic background is bigger than this value, that means it's upper this line, it means that you're actually able to distinguish the noise and the signals. So just for conclude, what we did, we actually did an estimation. We actually tried to understand how we can use the Null channel to see how different noise enter in X. And what we saw is that we are actually able to estimate the noise better between 30 and 1 milliards, because our estimate was up by a factor of 4 in power. And actually also there is, I don't want to give a very sad message, let's say, because the kind of detection threshold that we find actually told us that we are able to detect and distinguish between the noise if we have a big stochastic background. And actually that can also be helpful for us to rule out different models on the stochastic background. And in general, as I told you, we unfortunately cannot use the Null channel to do any kind of estimation on correlated noise. And I see that I'm already out of time, so I will stop here, and this is mostly my conclusion. Thank you.
Thanks, Martina, and thanks for reminding us that we actually cannot use cross-correlation for LISA unlike LIGO. It sounds trivial sometimes, but most people forget, and by people I mean me. Okay, so we have a bunch of questions. I will be greedy and ask my own trivial question. For the zeta, which gravitational wave source did you use?
We were considering a very simplified, let's say, stochastic background means that we are considering sources equally distributed along the sky, very simple sources. If you use many of them, they form a kind of stochastic background because they come from different parts of this, equally distributed for different points of the sky. And we also check our analytical computation with the GV response that was as you know, coded by Jean-Baptiste.
Mm-hmm. Okay, so I see a hand up. Quentin, go ahead and ask your question.
Yes, hi, Martina. Thank you for your talk. It's very interesting. So, of course, your job is to be pessimistic, right? Or at least to warn the unconscious data analysts that want to extract the stochastic backgrounds from the noise. I had a similar question as Sweta actually about the impact of the shape of the stochastic background you're considering, because you showed to us these upper limits of detection, but of course you have to take into account the integration, the integrated signal to noise ratio over the whole frequency band. So how do you take that into account, and which shapes are you considering?
Okay, so let's see if I understand the question. So on the right is the transfer function response. So the first one, so I actually really compute this formula. So for I do the difference between the noise. So in this case, sorry, let me see here. So this is really the noise of the instrument. So I cannot obviously do that because I don't consider I don't have data. Okay, so this is actually what we have, and this is actually what I was using. So this is really the noise of the instrument. So if you use LISA instrument, you just say turn on the optical metrology and the test mass acceleration noise. I multiply by this f, the zeta, and the f is actually the one that I show you. And then I divide it by these two transfer functions. And this transfer function, the first one is the transfer function of x towards a general stochastic background, isotropic. So I'm not considering any particular shape. I consider that I'm like agnostic from the kind of stochastic background I'm looking for. So it's not a deterministic signal. That is what you were wondering, or?
Okay, so you mean
I mean, I do the integration along all the frequency, along also all the direction.
Okay, and you assume it's white or constant PSD. Okay.
Yes, it's like white. It's actually white. Like the PSD is kind of one, like so, like a white constant, like a white noise. It's like a white noise.
Okay, understood. Thank you.
Okay.
Okay, so there's a couple of more questions. One is a yes/no question from Jean-Baptiste. What are you interested in a noise? What? No, why? Come on, Jean-Baptiste, get your English right. Why are you interested in a noise upper bound?
Okay, so you mean this red line? I'm interested in this because it actually tells us is a confidence level, because this noise upper bound is fixed. So it's not like floating up and forth if you have a signal, and it's something that you can actually estimate. So this is actually the data that we are going to have. And we know that we can use this upper bound, and we know that if we look, if for example, you take your instrument, you compute the PSD, and the PSD is more than this upper bound, you can say this is a stochastic signal, because it's actually the threshold that tell you this is a gravitational wave, this is not a gravitational wave. Obviously, it's not exactly this, because again, here just consider the noise here, not the signal. But you know that you can do this formula with your real data, and you know that if you, for example, you have X, and your X is bigger than this for you know this is a stochastic background. I don't know if I answered these questions.
That made sense to me. So we're already at time, but there's just one more question from Jean-Baptiste. I'll just read it, it's long. So when studying SGWB, how can you tell if an excess of power in X is due to the SGWB or another source of noise that we didn't consider? One, do you think there are other combinations that can constrain other sources' noise or discriminate easily between signal and noise?
Okay, so regarding the first question, I actually didn't read the last point. So we did this study just considering test mass acceleration noise and optical metrology noise. So we know from this upper bound that whatever is upper to this is a stochastic background. What we should do will be actually to include other kind of sources of noise like the tilt to length and so on, to see if actually they give you a different upper bound and something like that. So that's the main that's the main point that I cannot tell sure with just this noise that what we're going to see is a stochastic background, because I need to recompute including other noise. And regarding different signals, is a stochastic background or not? I think this is not our job, meaning that, so we are going to run a global fit, I suppose. And so for the other noise sources, I think they are going to have template to fit them. So the idea is that if you are able to fit also all sorts of all the other sources that you know, the leftover should be a stochastic background. And in order to know if it's a noise or if it's a stochastic background, you need to work by threshold.
All right, so thanks, Martina, for that talk. We will move
you.
on to the next one. We are already 2 minutes after. So our next speaker is Olaf HARTWIG. He is my former colleague from AEI, and he's now stationed in Cirte Theory Group in Paris Observatory. And he will tell us about the unimportance of clock synchronization for a certain frequency band in TDI. So Olaf, go ahead, please.
Yes, hello. Thanks for the introduction. Let me try to share my presentation. It works. Can you see my slides?
Yes.
Okay, perfect. Yes, so Sweta announced that we'll be speaking about time-delay interferometry without clock synchronization. This is present the results from a paper that I've been working on together with Jean-Baptiste, who's now at Glasgow, and Martin, who is also at the AI, and 3 colleagues from the CIRT, the Oriens, Marc, Lily, and Peter Wolf. And just a very short recap, we already heard a lot about TDI, so I will keep the introduction super short. As you probably know, TDI is part of the 0 to L1 pipeline, which takes as input 0.5 data, which is just the reformatted telemetered data, together with ground-based observation data like orbit spacecraft position tracking, and processes this data it gets processed by this pipeline to get L1 data, which are the TDI time series you use as input for the data analysis, and all the additional information you need, like clock desynchronizations and so on. And TDI is the arguably most important step of this pipeline, which reduces laser noise by many orders of magnitude. Now, as I said, we already heard a lot about TDI, but I want to remind of 2 important aspects for how it works, because that's the foundation for this work. And for this, it's useful to think of a simplified laser link, so not of the whole spacecraft, but just of the main components, which are in each spacecraft. You have a laser. This laser has some laser noise time series, just indicated by this little cartoon up here. And the laser of this spacecraft will be transmitted to the distant spacecraft and interfered there with a local laser on that spacecraft. The whole setup is pretty much symmetric. And this laser has its own laser frequency noise, such that the signal that we record on board the other spacecraft is simply the difference between the 2 laser frequency noise time series, where one of them arrives with a delay by the light travel time between the spacecrafts. We usually write that using such a delay operator. And to get an intuitive understanding of what's happening here, it's useful to look at a space-time diagram, where this is the word line of spacecraft 1, this is the word line of spacecraft 2. So the measurement that you record here will contain laser noise of that spacecraft at the time of reception, minus laser noise of a distant spacecraft at the corresponding time of emission. So that is what this delay operator does. It relates this time to this time. And of course, this laser link on its own, it will be completely dominated by laser frequency noise, but this goes away if you construct full TDI combinations, which look a bit like this. So this is the space-time diagram of the first generation max next combination, where you see that two beams are combined that were emitted from the same spacecraft at the same event. And you build this combination by simply combining measurements at the correct times, such that always one of these two noise terms that we had in our measurement cancels. And this is not a new idea. If you want to know about this specific interpretation of TDI in form of geometric photon paths, here are two references that explain that in a lot of detail. Now, my talk is about TDI with desynchronized blocks. So we try to understand how you can apply this algorithm. If you also take into account that each spacecraft has its own individual clock. And for this, it's useful to quickly recap what are the different timescales that you might encounter in LISA. One of them is the TCB time t, which is defined as the time shown of a perfect clock sitting at the solar system barycenter. That's a global timescale, and that's usually the one used for data analysis and for the standard literature version of TDI. We have the proper times of the three spacecrafts, which are the times shown of a perfect clock sitting in spacecraft I. They are related to the TCB time by general relativity, and they are very useful for describing the local physics inside one spacecraft. And finally, we have the actual onboard clock times for each spacecraft, which are the times shown by the actual physical clocks that are running in the spacecraft. Each spacecraft is equipped with an ultra-stable oscillator with a clock. And this clock gives you some timing signals, and these are the times that we can actually measure on the spacecraft. These are the only times that we can actually measure on the spacecraft, because all of these time frames up here are idealized times. And these differ from the proper times by instrumental imperfections of the clock. Now, to understand how you can do TDI, even if your data is given according to the spacecraft clocks, again, it's useful to look at the space-time diagram. Here, I will first walk you through a very basic TDI combination using data that is given in the TCB. So you start by combining two measurements at the same time, some TCB time TA. And as I mentioned before, you have to add to that measurements on the spacecraft 3 and spacecraft 2, the other two spacecraft, that are shifted by the correct amount, such that one of the laser noise terms, the one of the spacecraft 3 in this case, cancels out when you combine these two. And the time shift that you need to apply in this case, if everything is given in the TCB, is simply the light travel time, which you can compute from your estimates of the spacecraft positions together with the onboard measurements. And what you then get, if you form such a combination, is a virtual interferometer where two beams were emitted from the same spacecraft with a small time delay, such that the very typical formula for laser frequency noise applies. If this time delay is small, this looks like a derivative, and you simply get the phase noise becomes frequency noise, and it gets scaled by the time difference. This is not a TDI combination, it's a standard Michelson, but for a proper TDI combination, this is a very small number. Now, if you want to do the same thing using clock times, you can actually write down exactly the same space-time diagram. You again start with measurements given at some arbitrary starting time. But this time, these measurements are given according to the clock time, which are right here. Now, for laser noise to cancel, you need to add to those measurements measurements recorded on the other two spacecraft, time shifted by the correct amount. That again, the laser noise of the beam that was received here and the laser gun of the beam that is emitted here cancel out. And the time shift between these two times that you need to apply is now a pseudo range, which is something that we can actually measure directly on the spacecraft, because it is simply the difference between the clock time spacecraft 1 at emission, at reception, and the clock time of the other spacecraft at emission. Oh, there's a typo here. It should be tau 3 hat. Sorry about that. And physically, this corresponds to exactly the same interferometer. The only difference is that all the times are now given according to the spacecraft clock 1. But the crucial point is that if this number is very small picoseconds in the TCB, then it will also be very small expressed according to the real clocks. So laser noise will still be strongly suppressed in these variables. Now, this was the general idea, how it works. And now I want to speak a little bit about some technical details, how you can actually do that in practice and why it's beneficial to work directly in the clock time frames. And for this, first want to quickly recap how LISA actually measures the phase, what we actually measure. And as you probably know, LISA uses heterodyne interferometry, which means that we interfere beams at not exactly the same frequency, but with the 5 to 25 megahertz offset, such that the beat note signal that we get is a quickly oscillating beat note. And the gravitational wave signal is then encoded in the phase of the beat note, which is recovered from the phase meter, which is driven by a clock. I posted here a little graph of how these beat notes evolve over time. As you see, they are almost constant. They evolve very smoothly. And you also, on the scale of megahertz, you don't see any fluctuations in them. For this, you need to zoom in. So here I have another plot where I subtracted large trends from these beat notes. And you can see that they fluctuate by up to 100 hertz. This is laser frequency noise that we need to get rid of. And once we do get rid of this laser frequency noise, the gravitational wave will be encoded as a microcycle phase fluctuation, which in terms of frequency corresponds to about 100 nanohertz. One thing that's important is that laser frequency noise is not the only noise source in there, but one that is also quite significant is clock noise treated with these local clocks. The reason that is that, as I said, we have heterodyne signals up to 25 megahertz. They're oscillating very quickly. And to determine the phase, we need to compare them to a local reference clock. We do that in practice by digitizing the signal and then using a digital feedback loop. But the technical implementation actually doesn't matter. You always have to compare this oscillating signal to some reference clock. And if you want to reach microcycle precision in this comparison, it turns out that your clock needs to be stable to 40 femtosecond per square root hertz. And that is it's a much too stringent requirement for existing space qualified clocks. Such clocks simply don't exist at the moment. And one little detail that's important is that if you work directly with these large 25 megahertz beat notes, any time shift that you apply to them will also inherit that same timing requirement, because anytime you apply a time shift to your time series, you get the same kind of phase noise coupling. Just to give you an idea of how far away we are, here's a plot with some data from a clock measured by CNES. That's an ultra-stable oscillator, a quartz oscillator that will fly on the Power mission. It's not the atomic clock, it's a quartz oscillator. And as you can see, it's about 2 to 3 orders of magnitude above the requirement in the worst case. Now, that's a bit, so what can we do about that? The solution is to measure the clock noise and suppress it in the post-processing. And the way we do that is by using modulations of the clock onto the laser beam. So we have 2 of them. One of them is a so-called pseudo-random number code, which is just the sequences of 1s and 0s, which is modulated as a phase modulation to the beam. So it is a code that looks like this. And the second one is a high frequency modulation at 2.4 gigahertz. If you modulate a laser beam with such a sinusoidal signal, you get sidebands, upper and lower sidebands, which are indicated here. So instead of having just a carrier beam, you in effect have 2 more beams that you can use. And the whole setup is symmetric. So you have a 2.4 gigahertz sideband on spacecraft 1. You have a sideband at a slightly different frequency on spacecraft 2. And same as before, the spacecraft exchange their beams along the interspacecraft interferometer. They interfere. And you then get not just 1 beat node, but you get 3 beat nodes, 1 for the carriers and 1 for the 2 sidebands. And in addition, you also get the superposition of these 2 PRN codes, which you can then time shift against each other to determine the absolute range. And but it's important to point out that both of these signals, this clock signal and this PRN signal, in principle measure the same quantity. They measure the pseudo range because they are signals derived from the local clock. So in this beat node, the phase fluctuation in this beat node tell you about the relationship of this clock when it was emitted and the relationship of this clock when it was received. And this allows us to measure the pseudo range at a very high precision. What does very high mean? Here's a kind of plot where I show 2 more measurements provided by Michael Born and Kohei Yamamoto from AI. One of them is for the performance of the EOM fiber amplifier used in the laser prototype. And you can see that it is mostly within the requirement. It slightly violates it, at least this measurement still at the most critical frequency. And there are two reasons for that. One of them is just, it's very challenging to get it below that from what I understood. And the second one is that this requirement that I put here is very stringent at this frequency. So the requirement can be is relaxed a bit in the latest version. And I don't know if I think the laser also performs a little bit better, so we are okay for that. But it is a critical noise source. Whereas this divider here measured by Gohei is part of the electrical conversion chain. These different frequencies that we generate, they all need to, there's a long chain of conversions, but those are not dominant and they're subdominant with respect to the UM5 amplifier. But the summary is that these measurements together allow you to measure the pseudo range that we need for our version of TDI at the required level. And to summarize what we plan to do with that, so we propose a relatively simple pipeline where you start with your 0.5 data. You do some relatively simple ranging processing in which you combine the PRN code and the sideband to get a very high precision and accurate readout of the pseudo range. You then use that to compute your TDI combinations. And since our pseudo range is so precise, we can do that directly on the megahertz speed node and will cancel laser and clock noise in the same step. And what you then get are noise-free variables that you simply still have to time shift to the correct reference frame, but the required precision for that is much lower than for the full variable. This is in contrast to the standard pipeline, if you want, which has some more steps, because previously the idea how to do that was to first do the frame conversion and clock synchronization, to first put everything in the TCB, then remove laser noise. And in order to reach the required precision to do that, you have to remove megahertz phase ramps beforehand, which then implies that you also have to do an extra clock noise correction step. And I think I'm starting to run out of time, so I also started a bit late. But here's just one plot where we show simulation results that this actually works. So we tested that numerically using time domain simulations with realistic orbits, realistic clock noise, different clock offsets, laser noise, sandband noise, and PRN noise. And we also included the secondary noises. And you can see that we reach exactly the same performance as you would without any of these extra noise sources. So the dotted line here shows the model accounting just for the secondary noises and agrees perfectly with our fully processed result. And we also had a simulation where we turned off the secondary noises, and we see that we end up at the level limited by this previously mentioned modulation noise, which is also perfectly in agreement with previous results. So this pipeline really performs exactly the same. It's just simpler to implement. So this brings me to my conclusion. The main point is that you can construct TDI variables directly from unsynchronized data, that the necessary delays can be extracted from the onboard ranging measurement at the required precision, and this simplifies the pipeline. The resulting TDI variables still need to be synchronized to TCB, but at a much lower precision. And the second remark is that this version of suppressing clock noise by time shifting total frequencies was actually also experimentally demonstrated in the hexagon experiment that Gohei told us about in a previous session. And that's all I have. Thanks for your attention.
So thanks, Olaf. I must compliment on your view, the view graphs. They just keep getting better and better every time.
Thank you.
Okay, so I'll be greedy again and ask my own question. So what is this PHARAO stand for?
PHARAO?
You know, the real clock. Yeah, the PHARAO.
Oh, I don't know. It's a French acronym, I think. It's a part of the atomic clock ensemble in space. It's an atomic clock that they want to put on the International Space Station, but I don't know what it stands for.
Okay, and actually I had this question about, these are noise curves that are measurement of actual real clocks that are used in simulation, and then you run data analysis on it. And you know, we have this plan, right, to use the real clock data from hexagon into the data analysis. Don't you think it's a little bit going around the circle, repeating the same thing? This already maybe satisfies the study to conclude which clock to use, because the PSDs of these are actually measurement from real clocks. So what's the added advantage of using real clock in INREP, for example?
I think
it somehow feels to me like, this dog chasing its own tail.
No, I think it's not quite the same thing, because the measurement that I show here, it's a measured PSD of the very good space body USO, but I think the clocks that they actually have in the hexagon, they're not as good. They're less good. But I didn't take the actual time series of the clock. I got a measurement of the PSD, and I generate my own perfect Gaussian noise that has the same PSD, but it doesn't have any glitches, it doesn't have any artifacts. So there's a lot of idealizations in the simulation that you don't have in a real experiment.
All right, well, so there's no hands raised. There was one question I see from Alistair. I'd be interested to know more about the prototype laser in the plot. Was that a 1 watt or 2 watt?
I think it's 2 watt, this graph, but I'm not sure. You can reach out if you want to know the details to Michael Born from the AI.
I'll ask him on Tuesday.
Okay, so we are only 1 minute over time. Let's move on. So next up, we have Quentin BAGHI, who was in NASA Goddard, and he abandoned that to come back to France. So he's in the Française Atomic Energy Commission. He's very involved in LISA data challenges. But today he will tell us about blind cancellation of laser noise. So go ahead, Quentin.
Thank you. Can you see my slides?
Yeah, I can see your slide, but not your video.
Oh yeah, sorry. Yeah, I forgot to do that. Okay, here's my video.
Thank you.
Okay. Well, thank you. Thank you for giving me this opportunity to talk today. Hello, everyone. So yes, this is about blind cancellation of laser noise for space-based gravitational wave detection in general, and for LISA in particular. And this is a work that has been carried out with, yes, my Goddard colleagues that I abandoned, John Baker, Jacob Slesky, Ira Thorpe. So here today, I will give you a very quick overview of the state of the art of the time delay interferometry. Of course, I won't describe again what is TDI, because we had very good talks from Martina and Olaf before, so you know everything. I will focus on the idea that is behind this blind time delay interferometry technique that we've come up with, and I'll present some performance assessments and some perspectives for the future. So the idea, well, the objective is still the same, right? It's to fish for these very small gravitational waves, which are deeply buried into the laser noise. And the solution to do that was proposed by Trento and Armstrong in 1999. And since then, there have been extensive analysis of TDI, and including, you know, how to optimize the sensitivity, how to remove laser noise when arms are flexing, etc. And more recently, there have been studies about the several effects, and we've had 2 presentations about like the clock synchronization from Olaf, and also the construction of Null channels from Martina. And so there's been also other studies about the effect of filters, for example, from Jean-Baptiste. And this list, let's say, of studies shows us that TDI is not a trivial thing, right? And this is a crucial step for the mission that we have to study properly. And so that's good also to have some alternative thinking about it. And there have been different ways of looking at TDI already. There have been algebraic approaches, so, you know, considering TDI as a solution over the ring of polynomials by Vinet et al. In 2002. And then Romano and Wong in 2006 showed that there is a relation between principal component analysis and TDI. And then we've built on this idea recently. So there've been this new definition of TDR, numerical definition from the design matrix, which is to say the matrix that encodes how laser noise enters the measurements. And this is called TDI infinity. We separately proposed a derivation of TDI-like combinations from the laser noise covariance matrix. So it was a statistical point of view. And we did that in the frequency domain, allowing us to do data analysis and also TDI ranging. But then we kind of upgraded this idea to make it more model independent. And we come up with this data-driven principal component interferometry, as we name it, or PCI, and we demonstrated it with fixed arms. Since then, so it was in 2020, well, one year ago. Since then, we've developed this method, but to work with flexible arms. So meaning like to have the equivalent of second generation TDI. And this is what this talk is about. And here I want to stress the importance of, I think, of having this model independent technique. It's because it does not rely on any measurement model. It does not rely neither on the interspacecraft delay measurements. And therefore, it is robust to any modeling error, because if you have the tiniest error in your TDI combination, you may not achieve laser noise cancellation. And so we think that it provides a complementary check to conventional TDI, which is good to have for such a crucial step in the post-processing. Let me now present what is the idea behind this blind approach. And to do that, let's look first at what TDI does. It performs linear combinations of delayed phase matter measurements, which are tailored to cancel these laser noise terms. And here I have labeled in any TDI channel A alpha, which is produced by this linear combination, which involves, of course, coefficients and then delay operators that depends on the delay that themselves depend on time, and interferometric measurements, so phase measurements. And so in practice, of course, we have discrete data. So these delay operators have to be written down for discrete time series. And this is achieved with fractional delay filters, which have some finite half width NH. And basically, it's the number of measurement points that you need to perform your interpolation. And so this drives the accuracy of the interpolation. And so if you inject this, fractional delay filters into the first equation, you obtain the second equation with a fractional delay filter coefficients. And now the delay operator are just integer delays, right? You're just shifting your data by a fixed amount of samples. So if you gather all these this equation, or let's say all these integer time shifted data into a single matrix, a data matrix, you obtain this equation. So X here is the data matrix that contains the version of the data and the NH version of the data that are backward shifted, and NH versions of the data that are forward shifted. And so you can write this a very compact expression involving this data matrix X, and also correspondingly the vector of coefficients that I name here G alpha. So here you have the matrix of shifted observation and vector of coefficients. And the idea behind a data-driven principal component interferometry, or PCI, is to find some alternative to this TDI variable A, by exploring general combinations of the data matrix X. And these general combinations are informed by the data, looking at the correlations that are in the data. But how do we do that when we have time delay time dependent coefficients. So the trick is a bit like in second generation TDI, we have to approximate them by approximate these coefficients to tailor expanding them at first order in time. And we can get the same equation as before if we do that. If we redefine the data matrix X with this new data matrix Z, which contains X and X times the vector of time. So basically you have moved all time dependence into the data matrix, and you have now a constant vector of or matrix of coefficients G. So the aim then is to find a G from the data. And so to do that, we perform the principal component analysis of the data matrix Z, which is basically doing the singular value decomposition, Z equals U times S times V transpose, and S here is a diagonal rectangular matrix. And actually doing this operation is known in the data processing literature as singular spectral analysis, or SSA. And if you look at what are the singular value, you see that they can be ordered in decreasing amount of variance, so meaning that you are recombining your data, ordering them in according to the amount of noise that they carry. And we've done that for principal component analysis of 0th order in time. This was our previous work in blue. And now we've done that also for first order in time, which is shown in orange. And the idea is still the same, is to concentrate really on the lowest variance components and discarding all the other ones. And once you've done that, you can take your single link measurements, which are here in blue, dominated by laser noise. And so to generate them, we use the LISA instrument generator by Jean-Baptiste and Olaf and Martina. And this helps us to, allows us to construct this data matrix Z. And then we compute the singular value decomposition of Z and project the blue data onto the lowest variance components. And we obtain these orange and green results here, which are the principal projected principal components. In orange, you have the 0th order, and in the green, you have first order. So you see that you're suppressing some dominating noise here. But if we want to assess the performance of our algorithm, we need to compute the gravitational wave sensitivity. And that's, that's doable because any waveform that you have in the link measurements can be simply transformed using this linear, transformation. So you apply that to the Z matrix, the data matrix that contains the gravitational wave data, and you multiply it by V, and you obtain these principal component variables. And here we have, to check that, we have generated, actually, as Martina, stochastic point source in the sky with LISA GW response. And we obtained the blue curve once we transform it in PCI, sorry. And we have also overplotted this analytical model that we can derive from the same transformation, knowing the PSD of the injected signal. And so this allows us to then compare the gravitational wave sensitivity of first order PCI with the second generation TDI combinations. And so to do a fair comparison between the two, we need to adopt a definition of the sensitivity, which is maybe slightly uncommon, which is defined as the variance of the gravitational wave strain amplitude as it would be estimated by a generalized least square estimate. This just allows us to do a proper orthogonalization of both TDI and PCI, because maybe, as Mauro will tell us, the AET are not always orthogonal. So we want to make sure that we are dealing with orthogonal variables here. And so basically, with this definition of sensitivity, you have an expression like this. SH is given by this expression, but I won't go into the detail of that. So what we obtain when we do this computation, both for TDI and for PCI, is this curve, sensitivity as a function of frequency. And yes, for me, this is kind of mind-blowing because to compute the orange curve, we haven't used any information about how laser noise enters the data and what are the delays. And however, we obtain theoretically a very similar sensitivity as second generation TDI. So that's encouraging. And we decided also to check that with the simulation, so like empirical values. And so we actually, with this definition of the estimates of the strain amplitude at each frequency, we can produce time series of estimated strains as a function of time or as a function of frequency. We can convert that in the frequency domain. And this is what is plotted here. You have, so the blue curve is the same as before. This is this analytical sensitivity model. And in black here, you have the PCI data, which is computed with this least square estimate, and just projecting the single link measurements onto the principal components. And in gray, we have computed the TDI version of that with Pi TDI, which is this software developed by Martin Stab to produce second generation TDI combinations. And you see that they are very similar and follow quite closely the analytical model. So this is encouraging. And as a conclusion, I will tell that we developed a data-driven algorithm to cancel this laser noise with varying arm length. And we are simply performing principal component analysis on a data matrix that contains versions of the data that are shifted by integer numbers. And this is, we achieved that for varying arm lengths by including first order in time. And we obtained the same theoretical sensitivity as TDI, checked with a handful of simulations, but of course we have to check it more extensively by doing more simulations and also by constructing a laser noise residual model analytically. And we want to better probe the impact of the data size and stencil size, so this number of shifts that we use in the analysis onto the performance. We want to probe these hyperparameters. And but this is still an entirely model-independent method. And so in the future, we want also to demonstrate that gravitational wave parameter estimation is possible with PCI. And this is, I think, something which is required to fully convince people to use it. So thank you very much for your attention. And if you have questions, I'll be happy to answer.
So thank you, Quentin, and yeah, you cleverly sneaked in a crash course on matrix operations in your talk. That was very clever. So I don't see any hands raised. I saw some compliments for you. There was one remark I see from Jean-Baptiste. Maybe you should call first order PCI PCI2 because it's equivalent of TDI2. I have to agree to that.
What about calling TDI2 TDI1? No, I'm joking, but for me it made more sense to call it like that. But I agree, it would be less confusing.
Okay, all right. So we have two hands raised, but let me continue the tradition of just asking my own question first. So, what is, in your opinion, the best TDI algorithm if you want this operational on board? You are muted, Quentin.
Oh, I'm sorry. Sorry, wrong button. I mean, I think if you have a faithful, you know, modeling of your instruments and good accuracy in your estimates of the time or of the delays, I think that's good to use you know, classic TDI second generation, because you have a classic geometric interpretation and it's physically more understood. However, I think that, you know, if with in-flight data, for some reason, the first attempt in applying TDI doesn't work, then we have this, you know, second recipe to use to see if we can recover, like, I mean, if we can cancel laser noise, right? And that would, you know, give us hints or leads whether this is, you know, some instrumental problem or this is just some processing problem. So I think in that sense that the both are complementary, right? There is not something that is better than the other, I guess.
Okay, well, that was a bit dissatisfactory answer, but let's take the hand-raised question. So Olaf, please go ahead.
Yes, thanks for this. Very nice, very interesting results. I've seen them before, but still very interesting. At least part of them. I was wondering, what is the performance in terms of processing time for this version, for this processing compared to standard TDI?
Yes, so this is a few minutes. So actually, the performance it's more stringent. I mean, it's more demanding in memory than in CPU time. Like would be like to produce these plots, you have to wait like 1 or 2 minutes or 1 minute. I don't remember because yeah, because I use a lot of memory. But actually, sorry, because I have separated like the computation in several sub-computations. You can do principal component analysis in, you know, by stretch or by segments, and this allows you to not to eat too much memory. But I guess there are ways of speeding up the computation, you know, especially with more you know, adapted algebraic routines or with GPUs. I think we could do that very quickly. It's a bit like in TDI, actually. If you're you know, working out a matrix-based version of TDI, then you can make use of some fast algebraic transformations, right? Codes.
Yeah, okay, it's much faster than I thought. Thanks.
Okay, so we're already 2 minutes over time, but well, we don't need the entire 15 minutes for coffee break, right? It's overrated these days. So let's take Jean-Baptiste's question.
Well, sorry.
With an echo.
Okay, sorry about that. 2 mics, 2 speakers.
That's better.
Yeah, so you probably answered half of my questions, but just looking forward and looking to the analysis of gravitational wave in this PCI framework. Now you probably want to cut your data to only conserve the low variance eigenvectors, right?
Yes. Yes.
Is there a way, because these eigenvectors are fixed once you've run your PCA, is there a way to marginalize over their uncertainty, because you cut them to a certain point, so you made the decision basically on the way you write your likelihoods, or in another way to say it, you have a point estimate on your arm length. Can you include in your analysis the fact that there's some uncertainty in that?
So this is a good question. Actually, John Baker was thinking about that, like how to fold this into a Bayesian framework. So first of all, like to select your, you know, how many principal components you need, you can you know, compute your SNR or your sensitivity, and you see that after, you know, some number, like this is usually 6 for full sensitivity, or 3 for a good enough sensitivity, or like 90% of the sensitivity. Then you see that, you know, adding more components doesn't improve your sensitivity. So this is the first thing. And how to, I guess, I mean, the way we are, this is a linear transformation, so we should be able to assess the uncertainty of the principal or the, let's say, the elements of the eigenvectors, and then, you know, transform that into a Bayesian scheme where we are expressing the posterior distributions of these eigenvectors, and so you would get at the end some, you know, distributions of residuals of you know, laser noise-free residuals, let's say, something that you could do with TDI ranging. You know, I guess that was your idea.
Yeah, maybe.
Okay, well, maybe we can talk about that.
Thanks, Quentin.
Offline.
So wonderful. We ended up with a very engaging talk and conversation. So I thank all the 3 speakers, Martina, Olaf, and Quentin. And yeah, so we're 6 minutes over time, but that's fine because we only have 3 more talks to go. I say let's go for still our 15 minutes of deserved coffee break, and we meet here at 4:20